All right, so this short lesson will just deal with more questions involving function notation and domain and range. So again, just a reminder, when we look down here, I'm just kind of summarizing the idea of a function where we have a bunch of inputs, and the inputs, we call them the x values that deal with the domain. Okay, so remember, the domain is all the x values for a function. So here I have a x equals 2. So this is one input, right? So the function here, right, f of x equals x plus 1. If you remember, we talked about this being like the rule, right, that is going to be applied to any input. Right, so this 2 comes in here. And, right, we can show what happens, right, to the input of 2, right? So this is going to be 2 plus 1, which equals 3, right? So that is now my output, all right? And just remember that when we talk about inputs and outputs, right, like we have these ordered pairs, right? I have whatever the input is, I got the output, right? So I can write that as we have here, x and f of x. And then for our example here, the input is 2, the output is 3. All right. So if you have a good understanding of the input-output idea, then the remaining questions should not be too bad. Okay, so first example, given this function that we got here, we're going to determine these 3 things, A, B, and C. So notice here, you're given a function that is displayed as a mapping diagram. Okay. So we have here all of our inputs, here all of our outputs, and the arrows specify which input goes to the specific output. Okay. So if we let it rip, so we got A, all right, so A, so F at 4. So remember what F at 4 means. Well, what this means is, what is the output? Okay, remember, Y value, when the input, right, the X is 4. All right. So again, you have to understand the notation. And if you do, this question is like super, super simple. So then you say, well, okay, well, where is the input 4? And we look and say, okay, check it out. Here is our input of 4. And then you're like, well, where is it going? Well, the input of 4 is going to -3. So, right, f at 4, okay, my function evaluated at 4 equals -3. All right, and that is it. All right. So hopefully that wasn't too out there. So next what we'll do is we'll do one where I have to figure out what f of 3 is, but then perform some other algebraic expressions. So nothing too crazy. So I have 2 f at 3 minus 5. Okay. So what I got to do first, right, is we want to figure out what is f at 3. Okay. So again, this question builds upon the previous one. So if you got the first one right, then you're going to know how to do this one. Or at least you're going to know how to do the first step of this one. So I'm going to go back here and say, okay, let's find the input where x is 3. So that's this one. And then we kind of perform the same thing where I say, well, what where does the input of 3 take us? Well, it takes us to an output of 7. Okay, so that means that f at 3 equals 7. So now what we're going to do is we are going to replace f at 3 with 7. Now, what you just need to understand, like what the operation between 2 and f at 3 is multiplication, okay? So what I'm going to get here, right, we're going to get 2, and then f at 3, that is 7. So I'm going to have, so this is like 2 times 7 minus 5. And then now we just follow BEDMAS. So 2 times 7, that is 14. And then minus 5. And then now we just do the simple calculation. 14 minus 5 is 9. And that is that. All right. Everybody cool with that? Hopefully. Sorry, I'm asking students, I'm asking questions as if I'm actually talking to you. So that's B. And then let's do C. The value for A is such that f at A equals 7. So I'll just write this over here. Part C. Oops. Okay, so f at A equals 7. So again, here, A is the unknown. All right, so we have to figure out what A is, right? This is my unknown. And again, I'm going to go back to what the understanding of this notation. What does this mean, right? Well, this means what input gives us an output of 7. So again, when you understand the formation, you're like, yeah, or not the formation, sorry, I was watching soccer. The notation, really this question does not become that challenging. So now we're doing like the reverse. We're saying, well, where is the output 7? And if you have a decent memory, you may have realized that, oh shoot, well, here the output is 7. What takes you to an output of 7? Well, an input of 3. So for this question, right, my answer, right, A equals 3, right, because, right, f at 3 equals 7, which happens to be the answer we got for, right, like the one in part B. So again, the key is understanding the notation. If someone were to walk by the screen right now and look at the math we were doing, no one would really be freaked out because there aren't long solutions and like nasty looking things. Okay, the math is fairly straightforward. It's just because we're now doing math with a new notation. All right, so let's just practice that some more. So here we're given 2 functions. Now I don't think I've illustrated this kind of example, but so notice if I have 2 different functions, I have to change the letter. See here, like I have f of x, where f is my function. If I have another function, I can't call this one f of x, so we just change it to g of x. So again, you could have f of x, you could have g of x, you could have h of x, you could have any letter of the alphabet, a of x, p of x, whatever. All right. And we just introduce, this function g of x because it's different than f of x. So if I call this f and this f, then we're making some critical mathematical mistakes because clearly they are not the same. All right. So again, we're just going to practice some more questions that are very similar to what we did in the last one. So here I have f at 6. All right, cool. Now what am I going to do? Again, I'm going to take my function, right? F of x, which is 4x plus 3. And then wherever I see an x, I'm going to plug in 6. All right, that is 6 and that is 6. And then now we just perform the operations. What's 4 times 6? Well, that is 24. And then add 3. And then my final answer, 24 plus 3 is 27. So f at 6 equals 27. And that seems pretty straightforward at this point, I think. All right. So now we're going to do the exact same thing, but we're just using another letter of the alphabet. So really, if you've gotten through kindergarten and you know the alphabet, then this should not be that big of a deal. All right. So now I'm just using this function. So see where you could make a mistake. I mean, some students may copy this function, but we're using this new function, which appears to be a quadratic function, if you remember stuff that you did in grade 10. So now what we're going to do is just replace every x with -3. All right. And then here, now we just follow BEDMAS. We follow our order of operations. So again, don't go 3 times -3 because I have to do this part first, right? So -3 squared is 9. And then here, right, this, I'm subtracting a negative, which is the opposite. It kind of like the negatives cancel each other out. If I'm subtracting a negative, think of it, if I'm taking away cold temperature, then I'm warming it up. So this will be +3 plus 1, and then 3 times 9, well, that's just 27, plus, well, 3 plus 1, that is 4. And my final answer is going to be 31. All right. So hopefully that's all right. And then now we're going to do the same thing as we did in the last one. Just we're going to do, where I have to figure out what f at 5 is, and then just do some basic mathematics. So if we do part C, oops, let me just stay consistent here. All right, so it's 2 f at 5 minus 3, I think. Is it? Oh, I'm sorry. Minus 7. So again, what do we got to do? We got to figure out what is f at 5. So f at 5 is going to be, let's get our function, 4x plus 3. So it's going to be 4 times 5 plus 3, which is going to be 20 plus 3, which is going to be 23. All right. So now what we're going to do is we're going to take this 23 and put it in for f at 5. All right. So this is going to be 2 times 23 minus 7. And then we say, well, okay, 2 times 23, well, 2 times 20 is 40. And then 3 times 2 is 6. So this will be 46 minus 7. And that will be 39. Okay, and we're good. So hopefully you're kind of feeling nice about all this stuff. And again, you'll have some practice where you'll do ones similar and ones that are a little bit more, challenging. We'll see how we do. Here, well, let's look at this one. So we have we have a mapping diagram, and we want to know, is it a function? And then what's the domain and what's the range? Okay, cool. Seems okay. So all right, sorry. So is it a function? Well, again, for every function, there has to be, for every input, there's only one output. So let's look. 0 goes to 9, 1 goes to 4, 2 goes to 1, 3 goes to 0, 4 goes to 1, 5 goes to 4, 6 goes to 9. So here you could be, something could be, it could be tricky. Like, for example, if I look, like 0, like here I have 2 inputs going to 9, right? And you may think that's, illegal to pass as a function, but this is actually okay. Okay, why is it okay? Well, because 0 and 6 are different inputs. Same thing, if you look, 1 goes to 4, and then 5 goes to 4. So some students would be like, oh, this is bad. Or like 2 goes to 1, and 4 goes to 1. But that's okay, because there are no repeating inputs here. These are all different inputs, right? So again, if you look here, right, all of these inputs, these are all different inputs, right? So that means that, yeah, it's going to be a function. All right. So is it a function? Yeah, it's a function, because every input has exactly one output. All right. Now part B and C are domain and range. So if you remember, domain is what all the x values are. All right. So here, if you look, well, I mean, it's in a mapping diagram, it's fairly simple. Like, these are all the inputs. So the way I write it, remember, I do a squiggly bracket, and then we just write them in ascending order. And they are written already for us beautifully in ascending order. So it's going to be 0, 1, 2, 3, 4, 5, 6. All right. And then for the range, we do the same thing, just we're looking at the outputs, okay, or the y values. And if you look here, the range goes from 0, then 1, then 4, and 9. So we'll write that. And that is it. All right. So next what we'll do is we will kind of take our domain and range questions and look at it when we're checking out the graph of a function. Okay. First, what we're going to do is we're going to talk about something called set notation. Now, again, this is kind of an aside. If we were in a regular class, a semester class where we had more time, could kind of get into some interesting discussions about the different types of numbers that we study. But here, I'll just go over it really quickly. So the numbers that we use, or at least that I would imagine most of you have used in your mathematical studies, they're generally organized and categorized into different sets, so different classifications. So here I've written down a few of them. So like here we have, here the capital N is the natural numbers. So 0, 1, 2, 1, 2, 3. Generally we call them the counting numbers. Whole numbers are just the natural ones, but with a 0. Integers we call the letter Z. That's a symbol we use to denote that set. They're just the whole numbers, but with their negative counterparts. And then we have this one called real numbers, which literally deals with all the numbers, integers, fractions, non-negative, repeating decimals, all that kind of stuff. Now you may be wondering why we have to talk about real numbers. Well, because we do when we talk about the domain and the range of a function, okay? And you also may be wondering, what the heck am I talking about with real numbers? Because you're like, you probably are thinking, well, if there's real numbers, what? Are there imaginary numbers? And the answer is yes, there are. right? There are complex or imaginary numbers that don't belong in the set of real numbers. Moral of the story is that we're going to use the letter R to help us talk about domain when the domain of a function or the range of a function is, say, something like infinity. Okay? So if we look here, here is my linear function. Okay? The line y equals x. So again, every dot there, 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, and so on. And I draw the line to connect them. Okay? So when we talk about the domain, right, because the dots are connected and these arrows go on forever, then that means, well, I just kind of gave it away. That means this function goes on forever. All right? And it's going on forever like this way, right? So like this, shading it this way. It's going on forever this way, right? And then it's also going on forever this way. It's like, holy crap, okay? Like you get it. And it goes on forever this way. Okay? So you kind of get the point that I just shaded the entire grid. So I need to get rid of that just for our sanity. So how do I write that? If you're asked, hey, what's the domain of this function, this linear function? You're not going to sit there and write the squiggly brackets and write every single number, because we would be doing that until we die, because we'd never stop doing that. So here's how we do it, right? So again, we're going to use capital D instead of writing domain, and we're going to do a colon and squiggly brackets, okay? And again, every possible x value. Well, if I look at a line, like every single x value is allowed. Like it doesn't matter if it's in the positive x or in the negative x, right? If I pick a value here, is it on the function? Yeah, there it is. If I pick a value here, where is it? Up here. If I pick a random one here, where is it? There. If I pick a one here, it is there, right? In this pattern, if I go here, down there, here, like you get the point, right? So how do I write that x can be every possible, or the domain is every possible x value? Well, here's how we do it. So we're going to write x, and then we're going to write an e like this. It's like a cursive e, and then we are going to write the capital R, okay? And then squiggly bracket. So you know what x is, but let me just talk to you about what these letters mean. So this letter, this cursive E, is epsilon. Okay, it's a Greek letter, and it means like belongs to, or is an element of. Okay. And then this R, well, we just talked about those set notations, right? R is literally all real numbers, okay? So what this thing, this domain written using notation, what it means that x belongs to the set of real numbers, which is just a fancy way of saying that x can be any real number, can be any number, okay? And the same thing applies for the range. So let me just bring this up here. Right, for the range, we say, okay, I'm going to write R and then colon, squiggly bracket. Well, what about y? Well, y, if I pick any, like if I look, right, this is just going to increase forever. So I'm going to have infinite number of positive y values and an infinite number of negative y values. So we write the same thing, y, e, r. All right. And that is that. So for a line, a linear function, there are an infinite number of inputs and an infinite number of outputs. So hopefully that makes sense. And then lastly, if we look at this, I kind of forgot to erase this. So we're going to do the same thing, right? Here we have our function. Now this is a quadratic, which you probably remember. Well, I mean, you remember from last year. Okay. And notice how I'm calling this a function. Now, why is it a function? Well, we already did an example previously that passes, it passes the vertical line test, right? So it passes the VLT. All right. So now let's talk about the domain and the range. All right. So if you think about it, see how, like, same with just like with a line, right? This is gonna go on forever up here. So this parabola is gonna be, it's gonna, if you had a graph paper that was an infinite area, you could literally keep graphing. Because if you think about it, can you take any number and square it? The answer is yes, you can. All right. Like you could pick 1,000 and square it. You could pick 1,000,000 and square it. You could pick pi and square it, whatever. So that means if you think about a quadratic logically in terms of what the rule is or what the machine of the function does, which just takes a number and squares it, right? We say, oops, sorry. For a quadratic, right, x can be any real number. All right. Now the range, if you look, right, if you check out this graph, kind of like there is an area of the graph that unfortunately the function never goes, and that is down here. Okay. So I'll just shade it in just for, it's kind of fun for me. Oops. Oh, geez. Let me just undo that. Oh, God. Well, it was fun until I mess it up. But you kind of get the idea, right? Right. So here, right, the function is not allowed down here, right? Like if you look, it's not allowed. If it was allowed, then it would be down there. Okay, it's not allowed. Now, why is it? Well, think about it for a second. What happens when you square a negative number? Anybody? Hopefully you're thinking, well, if I square a negative, it automatically becomes positive. So that idea is pictured perfectly in this nice little graph here, right? And again, if I took here, if you see this little red man, right? Again, if I were to curse you and put you on this function, you could only travel here, like this way. You could not deviate from the function. Okay. So when I look here, what's the input? The input is -3. Well, -3 squared is 9. And then when I go here, right, input is -2. -2 squared is 4. -1 squared is 1. 0 squared is 0. And then my next input, I bounce back up, right? X is 1, output is 1. X is 2, output is 4. So if you were on this function here, you'd never get below the x-axis. All right. So how do we write that? Well, let's just think about it for a second. Okay. So range, colon, squiggly brackets. So again, I'm going to write, okay, so y is a real number, just because some mathematicians would freak out if I didn't say that at first. But then, so where is y? Well, okay, so y can't be negative. So how do I write that? Well, if y can't be negative, that means y is going to be bigger than or equal to 0, right? This number right here. Because 0 is the lowest value allowed. What's the highest? Well, we don't care what the highest, it goes on forever. Okay. So that is the domain of the quadratic function. This is the range of the quadratic function. Okay. And I believe that is it. All right. So again, I'll check out the news feed and there will be homework posted, all on Desmos, where you get some time to practice the concept we've studied, and we'll see you later.